So now we know how to calculate the parameters of normal distribution for the whole population. You have two parameters. It's the average mu, which gives you a center of the distribution, and you just take a sum of all your values and divide to the number of them. And then the variance or standard deviation, if you take a square root of it, which gives you an average square root distance between the values and the average. Well, what if we don't have a population, if we work with a sample? Okay. In this case, you cannot estimate the parameters because we assume that parameters are something that tell us about the population. In this case, you can estimate the statistics or characteristics of the distribution. Okay. And you remember that we use Greek letters for population, and for sample we use Latin letters. So that's how, for example, the estimation of average value will look like. So we use m instead of mu, and then we have a small n, which is a sample size. Okay. So you can see that the average estimation of average values is pretty much the same as for the population. You just take a sum of all values and divide it to the number of values. That's the variance, and again you can see that this variance looks very similar. So we use s instead of sigma, so it's s squared, and then we use again the small n. However, if you estimate the variance using this formula for your sample, this estimate will be a biased estimate. Why? Because the sample size is usually small, and if you use a small sample size, this formula doesn't give a good estimate for the population. To get a better estimate or unbiased estimate, you have to use this formula, which the only difference which is that you divide to n-1. Okay, you can think that if sample size is large, for example, if you have, I don't know, 100 or 1000 values, that doesn't make a big difference. If you divide to 1000 on 999, the value will be almost the same. But if sample size is small, then the difference will be pretty large. For example, if your sample size is 3, in the case of biased, you divide it to 3, but in the case of unbiased, you divide it to 2. So you will have like 1.5 times larger value. Why? Well, first of all, you can use this link to get a very good explanation from Han Academy, and we also will discuss a lot about we will talk a lot about the relationship between population and sample in the block 2. But meanwhile, I'll try to give a simple explanation why it's n-1. So I'll start with not very strict explanation, but from my point of view, a little bit more intuitive. Let's say that this is our population distribution. So we have a normal distribution. This is the bell curve, the normal distribution curve, and this is the average here. Well, let's say we take a sample, a small sample. Let's say the sample size is 3. So we'll get some values like this. Okay. If you repeat it again and again and again, of course, we will have different values. But the idea is that the smaller sample size is the smaller spread of the sample will be. And if sample size is really small, it will never spread as far as the real population. So it means that the standard deviation of this sample, if sample size is small, will be smaller than the standard deviation of the whole population. And by dividing to n-1, we sort of compensate the sample size, because if n is really small, then n-1 will stretch the standard deviation of your sample. The other explanation is related to a very important term in statistics, which is called degrees of freedom. Okay, degrees of freedom, ODF. Degrees of freedom is a number of independent random values in your sample. Let's say you took 5 glasses of water randomly from different parts of your lake and measure it, the concentration of chloride, and then you end up, for example, with something like 10, 15, 17, 23, and 25. Okay. So in this case, the sample size is 5. And because all 5 values are absolutely independent, they do not have any influence on each other, they were taken randomly and independently, the degrees of freedom will be also 5. Okay. Now let's say we need to calculate a variance, but to calculate a variance, first thing you need to do is to calculate the average, right? So we will take the average. It's a sample, so I use m. 10 plus 15 plus 17 plus 23 and plus 25. Okay. Then we divide it to 5. Well, we can calculate it. 10 and 15 is 25. 17 and 23 it's 40. Together is 65, and 65 plus 25 it's 90. So we have 90 over 5, which is 18. Okay, so this is the average. Now we calculate the variance by taking the 10 minus 18, square it, then plus 15 minus 18, square it, and so on and so forth, and then finally 25 minus 18, square it. It should be 18 actually. Now look, the variance depends on m, and then it depends on the values x, x1, x5. And because we are talking about random values, we assume that they are all independent. But it's not that anymore. Because now you can find, for example, x1 as 5 times m minus x2 minus x3 minus x5. So now x1 depends on the other 4 values, because we use the same values twice. We use the same random values first for calculation of the average, and then we reduce these values and the average to calculate the variance. And now we don't have 5 independent values anymore. We have only 4, and then the 5th value depends on these 4. Okay, so it means that we lose 1 degree of freedom. So in this case, the degrees of freedom will be equal to 4. Okay. You will see similar examples later in this course when we use the same fixed sample size, the same fixed random value several times, and therefore we lose degrees of freedom because we sort of reuse the same values for different purposes. It's like, imagine that you want to assess 5 different persons, for example, how good they write poems or something like this. And if you don't know these persons, if you know anything of these persons, you can be quite objective. But if you know them already, you will be biased because you will have some sympathy or anti-sympathy to some of the persons. So you will sort of know something about them already. So that's the intuition about this degrees of freedom and n minus 1. So now we can get back to our example, and then with this 10 glasses of water and finish all the calculations. We already know how to calculate the average. We just take a sum and divide it to 10 because we have 10 values, 10 degrees of freedom here. And then to calculate the variance, first we take a difference. So for example, if we look at the first value, the first difference is minus 13.4. It means that the value of 53 is 14 milligrams per liter smaller than the average. And then, for example, 15.12 is 15 milligrams per liter larger than the average. Okay, so you see that some of the values are pretty close to the average, like this one and this one. Okay, now we need to square the distances and take a sum. So that's the sum of squared distances from the average. You will later learn that it's denoted by SSXX, meaning sum of squares for centroid values. So you subtract the average. Then we can just divide it to n minus 1. So if you take 564.88 and divide to 9, which is n minus 1, you will get exactly 62.76. And then if you want to calculate the standard deviation, you simply take a square root of the variance. Okay. Very often, if your values follow normal distribution, you can just estimate these 2 parameters and describe your values using this short notation, meaning average plus minus standard deviation. It doesn't mean that all your values align inside within this interval. It's just a way to write something about the interval of your values shortly by using parameters of normal distribution.